Before we build a Microsoft PKI, we need its core ingredients. In this topic, you'll see how symmetric encryption, asymmetric key pairs, hashing, and digital signatures work together to protect data, prove identity, and make certificates trustworthy. You've already seen what PKI is, why organizations rely on it, and where Active Directory Certificate Services fits. Now we're zooming into the engine: encryption, key pairs, hashing, and digital signatures. Once these pieces are clear, the next topics, certificate structure, trust chains, lifecycle, and revocation, will feel much more straightforward. Public key infrastructure is really a trust system, and cryptography is what makes that trust believable. It keeps data confidential, so only intended parties can read it. It ensures messages aren't tampered with in transit. It proves who is on the other end, and it records who signed what, so actions can't be plausibly denied later. Encryption really comes in two families, and they solve different problems. Symmetric encryption is like sharing one house key. Both sides must already have the same secret, but once they do, it's very fast and ideal for bulk data. Asymmetric encryption uses a public key to lock and a private key to unlock. That split lets us prove identity, exchange symmetric keys safely, and create digital signatures, which is why PKI relies on it. Think of symmetric encryption as two people sharing the same key to a box. Once they've secretly agreed on that key, locking and unlocking becomes very fast. In most real systems, asymmetric cryptography is used only to set up a temporary session key. After that, the symmetric key does all the heavy lifting, encrypting files, network traffic, or database records. Because one key controls everything, key generation, storage, rotation, and protection are absolutely critical. Asymmetric encryption is built around a key pair that only work with each other. You freely share your public key, so anyone can use it to encrypt data to you. Only your private key can decrypt it, so confidentiality depends on keeping that key secret. Flip the process and you get digital signatures. You sign with your private key and others verify with your public key. PKI then adds certificates to prove that a given public key really belongs to a specific identity. In PKI, think of the public key as your open-facing badge, and the private key as your secret power. The certificate packages your identity with the public key, so others can encrypt to you or verify your signatures. The private key stays with you and is what actually decrypts data and creates those signatures. Both keys must match mathematically. If someone steals the private key, they can impersonate you and unlock confidential information. Private keys are the crown jewels of your PKI. First, keep them in secure storage. Use operating system protections, encryption, or hardware security modules so keys never appear in plain form. Next, strictly limit who and what can access them. Most services don't need direct key access. Certification Authority private keys deserve extra safeguards, approvals, and monitoring. If you ever suspect compromise, act fast. Revoke the certificate, generate a new key, and reissue. Not all keys are interchangeable. Each certificate includes key usage settings that tell software what that key is allowed to do. Some keys are meant to sign data or code, others to encrypt or decrypt data, and others handle key exchange or prove server and client identity. Microsoft certificate templates encode these purposes so administrators apply them consistently. Hashing is like giving any piece of data a unique digital fingerprint. You run the data through a hash function, such as SHA-256, and get a fixed-length digest. Change even a single character, and that fingerprint should change completely. That makes hashes great for checking integrity. If the hash matches, the data hasn't been altered. Unlike encryption, hashing is one way by design. You can't take the hash and reconstruct the original data. You can think of the hashing process as a simple integrity check. First, the sender hashes the original data and records that value. The data is then stored or transmitted. When it arrives, the receiver runs the same hash function. If the new hash matches, we're confident nothing changed. If it's different, something was modified, corrupted, or tampered with. Remember, hashing alone doesn't prove who sent it. Digital signatures add that identity layer. A digital signature is like a secure seal on data. First, the signer runs the data through a hash function. then encrypts that hash with their private key. That encrypted hash is the signature. Anyone can later recompute the hash, use the signer's public key, and check if the signature matches. If it does, the data hasn't changed and the signer controlled that private key. The remaining question is, do we actually trust this public key? Identity binding. A certificate authority proves it issued a certificate by signing it with its private key. When a browser or other client connects, it receives that certificate and validates the signature using the CA's public key. If any bit of the certificate has changed, the math no longer works and validation fails. Even with a valid signature, trust only exists if that CA chains up to a root CA the client already trusts. When your browser connects to a secure site, several cryptographic pieces work together. The server proves who it is with a certificate that ties its identity to a public key. Your browser verifies the certificate's signature and trust chain, then uses that public key to agree on fresh symmetric session keys. From that point, all data is encrypted efficiently. If any link is weak, expired, or untrusted, the connection is blocked. You've now seen the core building blocks of cryptography. Symmetric encryption protects data efficiently. Asymmetric key pairs enable PKI trust as long as private keys stay secure. Hashes prove integrity, and digital signatures bind identity to data. Next, we'll connect these ideas to certificate structure, trust, and lifecycle management.